Hello. So we continue with lecture 4B, capsule 4B, and we recall that we were in the fundamental lemma in linear algebra. The first fundamental lemma in linear algebra. V is a vector subspace of Rn. V is generated by k vectors. Then any set of k plus 1 or more vectors in V are linearly dependent. We'll prove this by induction on k. Assume that k is 1. So V is generated by a single vector V0. And I have picked up two vectors V1 and V2 in V. So V1 is a multiple of A, V2 is a multiple, V1 is a multiple of V0, V2 is a multiple of V0. If A is 0 or if B is 0, then the set V1, V2 contains the origin, so it's linearly dependent. So we may proceed by assuming that A not equal to 0, B not equal to 0. And then we see that BV1 minus AV2 is 0. And the coefficients B and A in this case are both non-zero. We only need one of them to be non-zero, but both are non-zero. Fantastic. So V1, V2 is linearly dependent. The induction base is established. Assume that the result is true for vector subspaces V generated by K vectors. Now we will have to consider we'll have to pass from the case k to the case k plus 1. So we shall prove it for the case k plus 1. So let us take a vector space V spanned by k plus 1 vectors v1, v2, vk plus 1. And we have to show that k plus 2 vectors in V are linearly dependent. So let us take these k plus 2 vectors w1, w2, wk plus 1, wk plus 2. Each of these w's is a linear combination of the v's. How many v's are there? K plus 1 v's. Which are they? v1, v2, vk and vk plus 1. So w1 is a11 v1 plus dot 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 plus a1k vk plus a1k plus 1 vk plus 1. So now I have written it deliberately the last vector in red. a1k plus 1 vk plus 1. Similarly, W2 is A21 V1 plus A22 V2 plus dot 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 A2K VK plus A2K plus 1 VK plus 1. The last term in this linear combination has been written deliberately in red ink, etc. WK plus 1 is likewise a linear combination AK plus 1 V1 dot 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 AK plus 1 K VK plus AK plus 1 K plus 1 VK plus 1. And the last vector VK plus 2 is AK plus 2 comma 1 V1 plus dot 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 AK plus 2 comma K VK plus the last entry is AK plus 2 K plus 1 VK plus 1. Now suppose that all the red terms are 0. Suppose all the red terms are 0. How, for example, the coefficients a1 k plus 1, a2 k plus 1, a3 k plus 1 dot 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 ak plus 2 k. Suppose they are all 0. Then what happens? The red terms disappear and W1, W2, Wk plus 1, Wk plus 2 are all linear combinations of how many vectors? K vectors. So W1, W2, Wk plus 2 lie in the linear span of V1, V2, Vk. And that's a vector space generated by how many vectors? K vectors. And so by induction hypothesis, they are linearly dependent. So that establishes the case when the red terms are all 0. So now we may assume that the red terms are not all 0. One of them at least is non-zero. And by renaming the vectors W1, W2, etc., I may as well assume that AK plus 2K plus 1, the encircled one, is a non-zero scalar. So once that is a non-zero scalar, what I'm going to do is that I'm going to try to use this AK plus 2, K plus 1, and I'm going to kill these things. How do I do that? I'm going to form a new set of K plus 1 vectors. W1, W1 minus this WK plus 2, I'm going to divide by this coefficient AK plus 2, K plus 1, and I'm going to multiply by this coefficient A1, K plus 1, and I'm going to subtract. So W1 minus A1 K plus 1 upon AK plus 2 K plus 1 WK plus 2. What will happen? This red term will disappear. This red term will disappear. Right? So, and so that will be a, so this W1 minus A1 k plus 1 upon A k plus 2 k plus 1 W k plus 2 is going to be a linear combination of only, these V1, V2, Vk. This red term has been killed. Similarly, do the other ones also. From W2 minus A2k plus 1 upon AK plus 2k plus 1 WK plus 2, etc., etc., etc. WK plus 1 minus AK plus 1 k plus 1 upon AK plus 2k plus 1 WK plus 2. All these things lie in the linear span of V1, V2, Vk because the red terms have been killed. And there are how many vectors are there in this list? K plus 1 vectors are there in this list. And where do they lie? They lie in the linear span of V1, V2, Vk. That is, they lie in a vector space generated by K vectors. They lie in a vector space generated by K vectors. So by induction hypothesis, they are linearly dependent. Because they are linearly dependent, because they are linearly dependent, there exist scalars C1, C2, Ck plus 1, not all 0. That is, at least one of them must be non-zero, such that the linear combination C1 times the first one plus dot 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 Ck plus 1 times the last one must be 0. At least one of these coefficients is non-zero. Okay, so now let us rewrite this whole thing. So this whole thing can be written as C1 W1 plus C2 W2 plus Ck plus 1 Wk plus 1 plus all the terms containing Wk plus 2 has been combined and their coefficients is some junk. I call it gamma. So now this last equation that you see here, C1 W1 plus C2 W2 plus dot 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 plus Ck plus 1 Wk plus 1 plus gamma Wk plus 2. I don't care what gamma is, it is some scale. That's 0. So I got a linear combination of W1, W2, Wk plus 2, and at least one of C1, C2, Ck plus 1 is non-zero. At least one of them is non-zero, so they are linearly dependent. So I have concluded that W1, W2, Wk plus 2 is linearly dependent, and the induction step is over. So this is the proof of the fundamental lemma in linear algebra. This fundamental lemma is going to be very important because we're going to use it over and over again. So I recommend that you study the proof of the fundamental lemma very carefully and before proceeding. Okay, because now the next thing will heavily depend on the fundamental lemma. So already the next slide is already flashed on the screen. The next thing that we proceed is basis and dimension. So dimension, as I said, is one of the most fundamental notions in linear algebra. It generalizes the intuitive geometrical idea that a line is one-dimensional and a plane is two-dimensional. So before we take up this notion of dimension, let us take up two conventions. The empty set, remember, is linearly independent. I already said that before and I'm repeating it here. Empty set is linearly independent. Now, if I give you a bunch of vectors v1, v2, vk, then you can form the linear combinations a1, v1 plus a2, v2 plus dot 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 plus ak, vk. What if the set was empty? What if you didn't have any vectors to begin with? What is the linear span of the empty set? So you might know from your mathematics that an empty sum is always given the conventional value 0. It's a convention. The empty sum, a sum where there are no summands, is assigned the value 0. What about an empty product? A product where there are no factors at all, that is assigned the conventional value 1. That is why 0 factorial is always assigned the value 1. An empty product will be assigned the conventional value 1. An empty sum will be assigned the conventional value 0. So linear span of the empty set is 0 and the empty set is linearly independent. Okay, these are the two basic conventions about the empty set. Let me just, I just recorded it. Now, just put it on the records. Now let us come to the definition of a basis. Suppose V is a vector subspace of Rn V is a vector subspace of Rn, then a subset S of V, a subset S of V is called a basis of V if two things happen. First thing that should happen is that that set should be linearly independent. Set should be linearly independent. And the second most important thing that should happen is that the linear span of S is V. S must generate V. S must be a generating set for V. So for the example of the plane, our example of the garden variety, V equal to X, Y, Z, column vectors X, Y, Z, such that X plus Y minus 3Z equal to 0. We have checked that S, if I take S to be 3, 0, 1 and 0, 3, 1, then these two vectors generate V, or these two vectors, the linear span of S is exactly V. Are these two vectors linearly independent? They are linearly independent because neither of them is a multiple of the other, or you can algebraically check it. A times the vector 3, 0, 1 plus B times the vector 0, 3, 1 equal to 0, 0, 0 will force A to be 0 and it will force B to be 0. So these two vectors, the set consisting of these two vectors is obviously linearly independent and the linear span is V. Now, so here is an example of a vector space and I have presented for you a basis consisting of two vectors. Another example of a vector space is a vector space consisting of the zero vector alone. Take the singleton consisting of only the zero vector. What is its basis? The empty set. The empty set is linearly independent and the linear span of the empty set is 0. So the zero vector space, the vector space consisting of the zero vector alone, has a basis, namely the empty set. Two examples are given you. Now you will ask, does every vector space have a basis? We are going to prove that every vector subspace of Rn has a basis. Every vector subspace of Rn has a basis, and we're going to prove that. Not only are we going to prove that, the basis is not unique. There could be several sets of bases. For example, let us take the plane R2. 1, 0 and 0, 1. These two vectors form a basis, correct? I can get any vector in the plane can be written as a linear combination of 1, 0 and 0, 1. But I don't have to take 1, 0 and 0, 1. Can I take minus 1, 0 and 0, minus 1? Of course I can do that also. So the basis is not unique. There could be several sets of bases. There could be several sets with this property that there could be two different, I can take two different sets S1 and S2 such that S1 is linearly independent and linear span of S1 is V. S2 is also linearly independent and linear span of S2 is also V. But so the basis is not unique, but what is unique is the number of elements in the basis. Not only not only will bases exist, they'll be non-unique, but any two bases will have the same cardinality. They'll have the same number of elements, and we have to prove that. And this common number, if you pick a basis and count the number of elements in it, that is called the dimension. We'll come to that. If V is a vector subspace of Rn, then two things happen. V has a basis, and any two bases have the same number of elements. They have the same cardinality. It is the theorem is completely obvious if V happens to be the zero vector space. There is only one basis, and that is empty set. And nothing more need be said. So let us assume that your vector space V contains a non-zero vector. So take such a non-zero vector V1. V1 is non-zero. Okay. The singleton V1 is linearly independent. The singleton V1 is linearly independent because V1 is a non-zero vector. And so if A1 V1 happens to be 0, then compulsorily A1 must be 0. So the singleton V1 is linearly independent. Now, you take the linear span of V1. You take all multiples of V1. That is, you take the set of all A V1 such that A varies over all the real numbers. And you call this the linear span of V1. You call this capital V1. Suppose capital V1 is the whole of V. Suppose capital V1 exhausts your V. Capital V1 is a subset of V. Capital V1 is a subset of V. But suppose if it happens to be the whole of V, That means that we got a basis, namely the singleton set V1 will be the basis. Other situation, capital V1 is a proper subset of V. If capital V1 is a proper subset of V, pick an element V2 outside of capital V1. Pick an element V2 outside of capital V1. Let us now first show that the bag containing these two vectors V1 and V2 is linearly independent. Suppose AV1 plus BV2 is 0. Suppose AV1 plus BV2 is 0. That means that, and if B is not 0, suppose if B is not 0, then I can rewrite this equation as V2 equal to minus A by B V1. But that's a contradiction, right? Because V2 is not in V1, right? And whereas minus A by B V1 is a multiple of V1, and so it is in capital V1. But we started out by saying that little V2 is not in capital V1. So that's a contradiction. What if B is 0? If B is 0, then we simply get A V1 is 0, but V1 is not 0, so A must be 0. So A V1 plus B V2 equal to 0 implies A equal to 0 and B equal to 0. So the set consisting of two elements V1 and V2 is linearly independent. And then now let us take the linear span of V1, V2. Take the linear span of V1, V2, call it V2, capital V2, call it capital V2. If capital V2 exhausts my whole V, capital V2 is surely a subset of V, but if it happens to be equal to V, that means that linear span of V1, V2 is the whole of V, and V1, V2 is linearly independent, so V1, V2 serves as a basis for V. Otherwise, capital V2 is a proper subset of V. Capital V2 is a proper subset of V. Select a V3 which is in V minus capital V2. Oh, again, there's a typo here. I'm sorry. This should be a capital V2. It should be a capital V2. Correct? It should be a capital V2. So select a V3 which is in capital V minus capital V2, and look at this three element set V1, V2, V3. They're linearly independent. Let us check that they're linearly independent. Suppose A V1 plus B V2 plus C V3 is 0. Then if C happens to be 0, then we get A V1 plus B V2 is 0. But V1, V2 are already linearly independent. So compulsorily A must be 0 and B must be 0. So all three are 0. On the other hand, if C is not 0, then I can divide this equation by C. And I can rewrite this equation as V3 equal to minus A by C V1 minus B by C V2. But that's a linear combination of V1 and V2. And the linear combination of V1 and V2 has been called capital V2. But therefore, we conclude that little V3 belongs to capital V2. That's a contradiction because we picked a V3 which is outside of capital V2. So we have proved that V1, V2, V3 are linearly independent. Now look at the linear span of V1, V2, V3. If you get the linear span of V1, V2, V3 is a whole of V, then that V1, V2, V3, the three elements set serves as a basis. Otherwise, pick an element outside that. So proceeding thus, we keep constructing vectors V1, V2, Vk such that the set V1, V2, Vk is linearly independent, and capital Vk, which is the linear span of V1, V2, Vk, if this happens to be the whole of V, then this set of k vectors serves as a basis. Otherwise, and if it serves as a basis, the process stops. Else, the process continues to the next stage. We pick a Vk plus 1, which is in V minus Vk, and we keep producing. And then again, you will and then you will say that V1, V2, Vk, comma, we throw this Vk plus 1 in the bag, and we get k plus 1 linearly independent vector. And the question is, can this process keep on continuing forever and forever? It can't. It can't continue. The process must terminate, and it should give you a basis. Why should the process terminate? In fact, not only the process terminates, we can tell you that the process must terminate in at most n steps. Because the process doesn't terminate in n steps, then it will go to the n plus first step and would have produced n plus 1 vectors in Rn, which are linearly independent. We would have produced n plus 1 linearly independent vectors in Rn, but Rn is generated by E1 cap, E2 cap, en cap. So Rn is a vector space generated by n vectors. So n plus 1 or more vectors are linearly dependent as per the fundamental lemma. So the process cannot continue beyond n steps. So before, either at the nth step or before, the process would have stopped and we would have gotten a basis for our vector space V. That completes the first part of the theorem, proof of the first part of the theorem, namely that if V is a vector subspace of Rn, then V has a basis. Now, the basis is not unique. So, but the basis is not unique, but its cardinality will be unique. Suppose that S1 and S2 are two bases for the same vector space. And suppose S1 contains K elements and S2 contains L elements. We know that the linear span, by definition of a basis, linear span of S1 must be V. Okay. And S2 is a subset of V because it's the basis of V. So it must be a subset of V. And S2 contains L elements. But we know that the linear span of S1 is V. S1 contains K vectors. So K plus 1 or more vectors are linearly dependent. But what do we know about S2? S2 is linearly independent. So S2 cannot, so the number of elements in S2 has to be strictly less than K plus 1. So it must be less than or equal to K. So L must be less than or equal to K. Reversing the roles of S1 and S2, we will conclude that K must be less than or equal to L, and we have established that K equal to L. So this proves that although the basis is not unique, any two bases have the same cardinality, and this number is called the dimension. So that gives us the next important concept. Let V be a vector subspace of Rn, and the dimension of V is the cardinality of any basis of V. The concept is well defined because any two bases have the same number of elements, and this number of elements in a basis is called the dimension of V. The dimension, the intuitive notion of dimension, has finally acquired a very precise mathematical meaning. Some examples, some exercises for you. Suppose you got three vectors v1, v2, and v3 in R3. Three vectors in R3 are linearly independent if and only if the determinant of v1, v2, v3 is non-zero. That's an amusing exercise for you. Please try to do it. What about two vectors in R3? Suppose I take two vectors in R3. When are they linearly dependent? If two vectors are linearly dependent, that means that one of the vectors is a multiple of the other. The two vectors are collinear. So can you use the cross product? If two vectors are collinear, the cross product must be zero, no? So the magnitude of the cross product must be zero. So I have given you a hint. So please do the exercise. Okay. So what does the exercise? Second exercise says two vectors v1 and v2 in R3 are linearly independent if and only if this determinant. See, if I take two vectors v1 and v2, I can take v1 dot v1, v2 dot v2, v1 dot v2, v2 dot v1, and I can form the 2 by 2 matrix. Vi dot vj. This is a symmetric matrix, no? Because v1 dot v2 is the same as v2 dot v1, and the determinant of this must be positive. Then the vectors will be linearly independent. If this determinant happens to be zero, then the vectors are linearly dependent. The vectors, I repeat, v1 and v2 are two vectors in R3. They are linearly independent if this determinant is positive. They'll be linearly dependent if this determinant is zero. Now you might wonder, can this be generalized? It's a general fact that if I take k vectors in Rn, then these k vectors will be linearly independent. If the determinant of vi dot vj, if I take vi and vj, I take the dot product of them and let ij vary between 1 to k, what do you get? You get a symmetric matrix. and you take the determinant. This determinant, and then look at the value of this determinant. If the value of the determinant is positive, these vectors are linearly independent. If the value of the determinant is 0, these vectors will be linearly dependent. In fact, this determinant has a name. This determinant is called the gram determinant of v1, v2, vk, or some people call it the Gramian. In fact, this gram determinant is related to the volume of the K parallelepiped in Rn. It's a square. It is a square of the volume of the K parallelepiped. Okay. So with this, I will complete, and I will stop with this lecture 4B. Now we are going to use ideas of dimension, basis, linear independence, and we are going to proceed to the next important concept, the rank of a matrix. The rank of a matrix is a very important notion in linear algebra, and we are slowly building up this grand edifice of linear algebra. The abstract theory of linear algebra is being systematically and gradually developed, and you will see it's a very powerful and a very versatile tool that you will have at your disposal, and which you can use in many problems in engineering and science and technology. So the rank of a matrix I will take up in the next lecture, and I will stop